o'clock, so we're going to start our first professional development webinar series. It's a joint collaboration between Deep Earth Academy and the National Ocean Sciences Bowl. So I'd like to say thank you for joining us tonight. I think it's going to be an exciting presentation. If you don't know me, my name is Melissa Burdor. I'm the program specialist with the National Ocean Sciences Bowl. And I get the privilege to introduce you all tonight to your presenter. But first, I'm going to go over just a few quick sort of housekeeping items. Just so you all know, you are on mute, simply so that everyone's going to be able to hear our presenter tonight. So when you have questions, which I'm sure you all will once we have Larry start presenting, if you could use the questions box on your webinar screen, you can type in a question and send it to us. And the NOSB staff will keep a record of those questions, and if there's a good time to jump in and ask one, we will. Otherwise, we'll hold all the questions till the end. So just to remind you, with this webinar series, the presentation is going to last about an hour, and then we have about 30 minutes set aside for questions and answers. So like I said, when that 30 minutes starts, I'll be sure to run through the questions that you've submitted. One other thing I'd like to tell you is there is a number for technical help. So just in case tonight you get kicked off or your sound isn't working or you can't see something, if you need to call the GoToWebinar folks, the technical help number is 1-800-263-6317. So keep that handy. And if you can also, if you start to have issues, you can send us a question about that as well. So again, thanks everyone for attending tonight. I see that our attendee list is still growing, so I assume that people are still going to be logging on. But as you can see tonight, let's see, I'll share my screen. Hopefully you can all see this. Tonight, our presenter is Dr. Larry Krissek, and he's from Ohio State University. And he's going to present tonight on ice ages and climate history. So the title is Reading Earth's Climate History from Ocean Sediments with an example from Pleistocene Glacials and Interglacials. So we're going to have Dr. Krissek start. So if you'll just give me 1 second, I will allow him to show his screen. Okay. Hopefully, Larry, you have control now.
I just clicked in. Can you see my screen?
I can, yes.
All righto. So can you see the PowerPoint now?
Yes. All
righto. Sounds good. Well, welcome, everybody. As Melissa said, my name's Larry Krissek. I go by Larry. And I will not be able to see any questions that you send along, so those will be collected by the folks in Washington, and if there's a chance, they'll put those in at the right time. Otherwise, we'll take care of as many of those as we can at the end of the session this evening. So welcome, and let's see how this goes. So I'm going to be talking today about the way in which we as marine geologists and climate scientists go about trying to read information about Earth's climate history from the past, from ocean sediments. And there'll be a little bit of a case study that we'll talk about towards the end that involves some work that I've done that's been looking at a way that Pleistocene ice ages is recorded in the sediments, or are recorded in the sediments. A little bit of an outline. We'll start by trying to make sure that we're familiar with what kinds of things, what kinds of parameters are the sorts of things that we consider to be indicative of climate in the ocean. If we talk about climate up on land, there are probably certain things that we all think of, but what would be the equivalents of those when we're out in the ocean? And once we find out what those parameters are in the ocean, we might also want to be clear on what those parameters can affect that are important in the way that the oceans work And we're going to especially focus in on the ocean climate for the surface part of the ocean. There are some things that we would consider climate and climate-related that work in the deep ocean as well, but in the interest of time, we're going to restrict ourselves primarily to the surface ocean tonight. And once we have a sense of what those effects might, or what those responses in the ocean itself might be, we'll talk a little bit about how those responses can be recorded in one way or another in the sediments, so that thousands or tens of thousands or hundreds of thousands or millions of years later, we come in and collect some sediments and try to tease out what the climate story is. And this is the place where we'll introduce ourselves to what are referred to as climate proxies. So these will be certain characteristics or compositions in the sediments that, if we have a little bit of background and some understanding, we can interpret as a climate record, because there are not direct records of climate. There are only these indirect records of climate in the sediments. And then the example that we'll look at in a little bit of detail is the input of material from land into the ocean carried by icebergs. And this is what's referred to as ice raft debris, or we use the abbreviation IRD. And I'll talk a little bit about some work that some students and I have done on sediments from the North Atlantic. And these tell us a bit about the history of glaciations over the last 1 million years in that part of the world. All right, so let's start by just recognizing that records, geologic records that we interpret to tell us something about climate change, are actually very common out in the world. I live in Ohio. I'm not sure where everybody who's listening in tonight lives, but I'd imagine that at least some of you are from, say, the northern half of the continental U.S. And you may have a story of climate change in your part of the country that's similar to the most commonly recognized story of climate change that we have here in Ohio. And that's the story of the ice coming into the state sometime during the last million years or so. And the map that you're seeing here is what's referred to as the Glacial Map of Ohio. It's produced by the Ohio Geological Survey. And your state geologic survey, whatever name it goes by, probably has produced a similar kind of map if you live in a part of the country where there has been glacial influence. Now, the map says it's the glacial map. It's not actually the map of the glaciers. It's the map of the sediments that were left behind by these glaciers. And in Ohio, let's see, hopefully you can see my cursor. In Ohio, the ice actually did not occupy the entire state. It stopped not too far into the state up here in the northeastern part of the state, and then it extended farther south in the central and western part of the state. So if you notice this pattern of colors, the eastern and southeastern part of the state, which I'm outlining now, is mostly this sort of pale yellow color. And that pale yellow represents the materials that are not ice-influenced deposits. If you go to the northern part of the state in the northeast, or you go through most of the rest of the state in the central or the western portion of the state, you get this mosaic of colors. And those colors are of a variety of different kinds of glacial deposits. And the details of that are not really important to us right now. I think it's useful to demonstrate that this is a record of climate change that's carried by the geology, in this case, in the state of Ohio. And from my experience talking with school groups, even by middle to late elementary school, or definitely by middle school, the students will have heard and at least be able to repeat back that 18,000 years ago or so, Ohio was under a mile worth of ice, and it's not there now, so there must have been some climate change. In this case, the part of the climate story that we're talking about is the ice volume story, the presence or absence of glaciers. And what we'll find as we go forward is that different kinds of proxies in the sediments tell us about different components of the climate story. So we always have to worry about what part of climate we're actually reading. Then the other concern we have when we're trying to put one of these records together is how complete is it? And if you look at the bottom of the map, you'll notice that there are sort of groups of colors that sit in columns, and at the head of each column there's a name and some ages. And so here on the left we have what are known as the Wisconsin or Wisconsinan deposits, and then we have next over these things called the Illinoisan deposits. If you just do a quick look at the colors that are here under the Wisconsinan and you look up at the map, you'll see that most of the glacial deposits in Ohio are Wisconsinan in age. And that's the record of the last made at ice advance and retreat. The only places where we get some of these older deposits, the Illinoisan or the pre-Illinoisan, are down here around the edges, where, in fact, the Wisconsinan ice didn't go. So the Illinoisan ice extended farther out than the Wisconsinan ice. And so the only place that we see that older material is actually where the younger ice advance didn't erode it away. So a problem that we face when we try to do paleoclimate research on land is that the record is often not very complete. And that's why we then tend to go out into the ocean basins where the ice doesn't tend to have as much of a direct effect, and it doesn't do much in the way of eroding. The drawback of working out in the ocean on this sort of story is that you're often farther away from where some of the events took place. So it's a little more difficult to directly link what you're seeing to a particular change in the climate system. But the picture that you're seeing here is a picture of the drill ship, the Joides Resolution, which has been used since about 1985 for scientific ocean drilling throughout the world's oceans in a program known as ODP, or the Ocean Drilling Program, and now a program called IODP, the Integrated Ocean Drilling Program. And quite a few of the cruises of the Resolution in the last 25 years or so have had a focus of studying Earth's climate history of the past. And that'll be the source of some of the things that we'll talk about later. Now, some of you may know that there was a predecessor to ODP, which took place from the late 1960s up to about 1983, and that project was known as DSDP, or the Deep Sea Drilling Project, and it used a different ship called the Glomar Challenger. And it was really due to some technological advances late in the time of the DSDP program that we started to have records that we could look at in order to interpret Earth's climate history in some kind of a fairly complete way. So this ship has been the source of many of the seafloor cores that have been used to study Earth's climate history. All right, for those of you who aren't necessarily familiar with ships much, sorry, let me back up for a second. The Joides Resolution actually started out life as an oil drilling ship. So it has the drilling derrick here. It has equipment that allows you to put together long pipe that goes into the seafloor and lets you recover your cores. Underneath that derrick is the drill floor itself. And here's a picture of the drill floor with some of the roughnecks moving some of the piping around. The place where the pipe actually goes into the ground is underneath this red circular table. And we depend on the drillers and the roughnecks a lot to get us good quality core. This is a slide or a picture showing one of the cores, a sediment core, that's just been taken, and the drill floor is back up through that doorway off in the distance. And the technicians here are bringing out a core. In general, the core will be about 9 to 9.5 meters long, and the core is this plastic tubing, which is now all filled with sediment. One of the advantages of some of these techniques that are available now is that they give us long cores. They give us cores without any big gaps in them, which is good because that lets us put together a fairly complete story. And the sediment in the cores itself is in good shape. It hasn't been squished and squeezed and abused during the coring process. Now you might imagine, and you'd be right, that trying to move a 9-meter long piece of spaghetti like this around on a ship is a little bit difficult. And so the first thing that's going to happen will be that the Cortex will lay the core out in a series of holders here, and they'll come in and they'll slice the core or cut the core into pieces that are 1.5 meters long. And then they cap the ends of those sections to make sure that everything is marked so we know which section goes next to which section in order to reconstruct the order, the correct order of the sediments. And then we go on from there working with those 1.5 meter long sections of core. All right, so the core would, oh, hello. I'm having a technical issue here, so give me just a second. Well, this is not good.
Is it not advancing to your next slide?
Yeah,
or?
It's not advancing to my next slide.
Let's see.
Well,
Okay, from my end, it's still showing you as the presenter. I can
okay.
I can try to change it back to my screen and back to you to see if that. Let's try that quickly. See if that helps.
Okay, let's go to you.
Okay, now let me try one more time.
Let me see if I can get this. Oops, okay, it's advanced. So if you send it back to me, maybe.
Okay, let's see if it works now.
All right.
The multi-sensor track
Yep.
photo?
Mm-hmm.
Okay.
All right, well, let's cross our fingers and hope that this keeps going then. So in this case, you're now just inside the laboratory complex on board the ship, and these tubes that you see are actually the 1.5 meter long sections of core. They're filled with sediment, and although you can't see it, they're marked so we know which section goes on top of or below which other section. And these sections are being run through what's called a multi-sensor track, which is a series of pieces of equipment. You can actually see them back here on the right. That'll slide up alongside this track and make some measurements of the core. And so we know something about the core even before we open it up and take a look at the sediments. All right, after the core's been scanned with the multi-sensor track, each one of those sections is then cut in half lengthwise. And what you're seeing here are images taken of 1/2 of each of those sections. So for this particular core, section 1 would be the uppermost 1.5 meters, and the base of section 1 would sit directly above the top of section 2, down to the bottom of section 2, the top of section 3. And so this is the way that we can handle the core more easily in the confined space of the ship. Now, one of the reasons I picked this set of pictures is that I hope it's fairly clear that there are different kinds of layers in here. Some of them are dark, some of them are light, some of them are brown, some of them are brownish red. And so that pattern of layering is very useful to us. You can think of those layers as being kind of like pages in a book. And as long as we can see the pages, that helps us in establishing a time order for events that we're going to read. The color changes that you see in this core are actually related to changes in the composition of the sediments. So the composition of the sediments may be telling us something about climate or other things going on in the ocean. And the third point that I'd make from these slides is that those layers, they may be a little bit bowed, and that was caused by the coring process, but at least the layers are still stretching horizontally across the core, which tells us that this sediment was treated fairly gently as it was being cored.
Larry,
All right.
may I jump in quickly?
Sure. Yep.
We have one question. They're asking, what does the multi-sensor track actually measure? Geophysical properties?
Yeah, it generally measures 3 different properties. One is how quickly a sound wave passes through that material. And we use that information in order to be able to read some of the measurements that were made in the area before the core was ever taken. Before any one of these cores is taken, there will be a lot of what's known as seismic reflection data collected. Think of it as being kind of like a sonar on steroids, where the sound waves have enough energy to bounce into the seafloor and come back from different layers. And if you want to convert the information that you get from seismic reflection from how long it took for the echo to come back to how deep the layer is that caused the echo, you need to know how fast the sound travels in the material. So that's what's called the P-wave velocity. Then there's a device on there that measures how much what's called porosity there is in the sediment. Porosity would be the pores are the open spaces between the grains which are filled with water. So there's a tool that can measure how much porosity there is. And then the third measurement is something called magnetic susceptibility, which is not the same as the paleomagnetics that you would use if you're trying to tell, for instance, the magnetic quote-unquote stripes or anomalies on the ocean floor. Magnetic susceptibility simply tells you if you put this material into a magnetic field, how does it respond? So it's used to get an estimate of how much magnetic mineral might be in that part of the core. Okay?
Yes, thank you.
Sure. Okay, so that's the story of the completeness and why we go out to the ocean to get these records. Now let's think about the aspects of the ocean, and especially the surface ocean, that we might think of as being climate related. Well, on land, one of the components or aspects of climate that people think quite a bit about is temperature. And we could argue about whether you'd want to use the annual average temperature or the average high temperature, or which in detail you're going to use. But out in the ocean, the equivalent would be sea surface temperature, which is usually abbreviated as SST. On land, when we're worried about climate, we also often worry about how much water is available, so precipitation and evaporation. If we're out in the ocean, the surface salinity of the ocean actually tells us something very similar, how much precipitation there is versus how much evaporation. On land, we also often characterize a climate based on the winds, their positions, how strong they are. Out in the oceans, the equivalents would be surface currents, and depending on what the currents are doing and how they interact with the land surface in some areas, you may have this physical process called upwelling, which can be quite important, and we'll talk about that again a little bit later on. And a final component of what we might think of as climate on land is how much ice is around, glacial ice volume, or how much area is covered, so what's the extent. We have a similar interest out in the ocean. We're interested in glacial input, primarily by calving icebergs. But we're also interested in the presence and abundance and distribution of sea ice in the ocean, where sea ice is frozen seawater, and sea ice can have a really major impact on what we could think of as the climate of the surface ocean. All right, just to link this back to some things you may have seen before, if you've looked at almost any introductory oceanography textbook that's out there, you'll see some kind of a map of sea surface temperatures. In this case, the upper picture is for the northern hemisphere summer. The lower picture is for the northern hemisphere winter. But it shows the distribution of present day warm waters near the equator and cooler waters at high latitudes. And so if we're looking into the past, we'd be interested in knowing what was the sea surface temperature at that time compared to what it is today. This is a map. You might have seen it or similar, depending on what introductory oceanography text you may take a look at. But this is showing the areas that today are affected by a process we call coastal upwelling. When you have the winds blow in a certain direction along a coastline, the water, surface water, can be pumped offshore. And what's especially important about that is this brings some deeper water close to the surface. And with that deeper water comes nutrients. Those nutrients come into the lighted zone, and we have lots of biological productivity. You may have heard stories about the Peru-Chile coastal upwelling system. That's probably the one that gets the most talked about and written about. All right, so these components of climate in the ocean, temperature, salinity, and the like, what do they actually affect? In terms of sea surface temperature, as we move waters around in surface currents that have different temperatures, that does a lot for transporting heat. The temperature also has a direct effect on the density of the water, and the density of the water is going to control whether the water stays at the surface or sinks or mixes in some vertical way. And sea surface temperatures also have a strong influence on the distribution of planktonic species. We'll especially be worried about certain kinds of microorganisms that have produced skeletons that we can find in the sediments, and also pelagic species, so these are free swimming but up in the water column. Surface salinity has an effect on the rate at which seawater can be evaporated. It can also affect seawater density, and some of our planktonic organisms and pelagic species are salinity sensitive, so their distribution will be affected by where the water is slightly more salty or slightly less salty. Surface currents and upwelling in the ocean also can have an impact on heat transport. It can also influence the distribution of nutrients, and if we change the distribution of nutrients, or we get lots of nutrient into the surface waters, then that will have an impact on the distribution and amount of productivity. And if those producers are making skeletal material of some sort, whether it's biogenic silica, what we call opal, or it's calcium carbonate, if we have lots of these producers around, then we're likely to have those kind of particles in the sediment. Glacial input, particularly by meltwater and calving of icebergs, that can put fresh water into the ocean. If we do this in a large scale, so go from having a continental scale ice sheet to having not much ice up on the continent, when we return that water into the ocean, it can actually affect what's known as the oxygen isotopic composition of the water. Glaciers can bring in lots of sediment to the ocean, and in some cases they can also supply nutrients. And finally, sea ice has a really big influence on the exchange of heat from the ocean out to the atmosphere. When you make sea ice, when you freeze seawater, most of the salt actually gets excluded from the ice, and so the remaining water gets more salty. This is known as brine production, and producing brines has a really big impact on what happens in the deeper parts of the ocean. And there are actually certain kinds of plankton that do best when they're underneath or close to sea ice, so there can be an impact from sea ice on the distribution and abundance of life. Okay, so those are some of the components of what we might consider ocean climate and the effects that they can have on certain kinds of processes in the ocean. But how can we read these out of the sediments? This is our introduction to climatic proxies, or characteristics within the sediment that we can use to say something about climate at times in the past. I've subdivided these into 4 categories. The first is characteristics of the whole core. There are certain sediment types that just by themselves tell us something that is climate related. In some cases, the color of the sediment can actually be telling us about composition, and in a similar way, give us a record that is climatic, can be interpreted in a climatic sense. We also have proxies that are based on the biology. We'll talk briefly about a couple of cases of what could be considered indicator species. So species that have pretty close links to certain kinds of environments. And so when we see those indicator species in the sediments, we know that a certain environment, which is often climatically related, existed at that time. There have also been more complicated sort of statistical methods, these things called transfer functions. We're not going to talk about those. There are a lot of these proxies that are based on chemistry in one way or another. And one that we'll talk about briefly will be stable isotopes of oxygen, particularly as that record gets contained in the shells of a kind of plankton called foraminifera, or forams. And I noticed on the schedule that later on Brian Huber from the Smithsonian will be talking, giving one of these webinars. And Brian's specialty is working on forams, including the stable isotope record. So you'll hear quite a bit about that later on, I suspect. In some cases, the geochemical proxies are actually ratios of certain elements. Some plankton will incorporate a little bit of magnesium or a little bit of cadmium or a little bit of something else into their shell, and how much they incorporate depends on the temperature of the waters where they're living. So some of these elemental ratios get used as proxies. And finally, we have these proxies that are called terrigenous proxies. Terrigenous particles are the ones that started on land, thus the terra, and have been brought into the ocean in one way or another. And a number of these different kinds of land-derived particles have been interpreted with a climatic story in mind. The one that we'll talk about particularly later on will be this material called iceberg-rafted or ice-rafted debris, or IRD. Okay, so let's look at some specific cases. This is a slide that shows two parts of two cores, or two parts of a core. This core was actually drilled close to the continent of Antarctica. And if you look at the diagrams that are here down at the bottom, the sort of logos for this project, which was called Andrill, you'll notice that the drilling, this is the drilling rig, the drilling rig was actually sitting on floating glacial ice, what's called an ice shelf, and went through the water column and then drilled into the seafloor. So this is a non-conventional drilling platform. Because of the ice, the standard drilling ship, the Resolution, couldn't go to this area. So we used a different technique that involved putting a small drill rig up here on top of the ice, going through about a half mile of water and then drilling into the seafloor. I do want to point out that today, where the drill rig was located, is covered by about 80 meters of glacial ice and then a half a mile or so worth of seawater before you get into the seafloor. But in this core, as we were drilling it, we came across some sediment types that we didn't expect. This sediment type shown in the picture on the left, this is part of a core that is a kind of sediment called diatomite. It is essentially all diatoms. So there are literally billions and billions of diatoms in the sediment that's shown in this picture. And in order to have that many diatoms, which are algae, primarily that live in the surface waters and produce there, in order to have that many diatoms around, you needed to have open water rather than this ice cover, and you needed to have high productivity. Now, also in that core, in other intervals, we have the kind of sediment that we see on the right-hand side, which is a glacially deposited sediment. It's got some bigger pieces and it's got some little pieces. They're all sort of jumbled together. This is the classic kind of glacial deposit that some of you may know that we refer to as a till. And some of the pieces that were in that this could be up to 2 meters in diameter, or at least 2 meters length within the core. So we know that there were big boulders as well as some of these littler pieces that were being moved by these glaciers. This is a cartoon that shows the sediments that we recovered in the upper 500 meters of that core. And so the left-hand panel is the core from the surface down to 100 meters into the seafloor, then 100 meters to 200 meters into the seafloor, 200 to 300, and so on down to 500 meters. What's important to us here is that these areas shown in yellow, those are diatomites. The areas that are shown in the green, like this, are the glacial deposits. And we go from sediments about 1 million years old there to about 5 million years old down here. So 4 million years represented by 400 meters of sediment. And we see evidence of the water being open, then covered with ice, then open, then covered with ice, open, covered with ice. So this carries a paleoclimatic story with a lot of advances and retreats of the ice across this area. Prior to us drilling this core, one of the major ways that the climate history for that part of Antarctica had been interpreted was that it had been frozen in a big ice sheet more or less continuously since 15 million years ago. So just seeing the sediments like the diatomites tells us that that's not the case. All right, sometimes sediment color by itself is an indicator that carries paleoclimatic significance. This is a photograph put together from a series of smaller bits for 9 meters of core, and this is from a site in the North Atlantic, a little bit south of Greenland. And although the colors are a little bit stripy here, I hope you can notice that there are bands that are relatively lighter. So a little bit lighter here, a little bit lighter there, a little bit lighter there. The red line and the yellow line, these are actually some of the data that come from that multi-sensor track. And so you can see that the multi-sensor track is, in its own way, for each one of these signals, recording some kind of a change that corresponds to these color changes. Well, what we know, or what we knew going in and has been confirmed, is that these lighter bands are enriched in carbonate. But this isn't carbonate that came from plankton. This is carbonate that was actually eroded from limestones on land, especially in the areas around Hudson Bay, and was brought out to this area and other places in the North Atlantic by a big flush of icebergs. And we may get a chance to talk about some of that later on. In other parts of the ocean, though, similar changes in color have been linked to carbonate that comes from plankton. And so if you're seeing more carbonate and less carbonate, that might be telling you about more productivity in the ocean and less productivity in the ocean, which itself can be, in many cases, linked back to climate. Okay, now looking at some biogenic proxies, or biological particles. These are photomicrographs of diatoms, and for true scale, these diatoms would be about the size of say a small to medium grain of sand. Now, the diatom on the left is a diatom called Eucampia antarctica. It has this characteristic shape. I refer to it as the Viking helmet diatom. And I'm not a diatom specialist, but even I can identify Eucampia antarctica because it's so distinctive in its shape. But Eucampia antarctica is one of these diatoms that has a very distinctive habitat that it lives in. It only lives beneath sea ice. So if you're looking in some sediments and you find Eucampia antarctica, that's telling you that there was sea ice present at that time. Now on the right-hand side is one of a genus of diatoms called Thalassiocyra. And Thalassiocyra lives in more normal open marine conditions. So in a sediment core, if you were seeing a layer with Eucampia, and then a layer with Thalassiocyra, then back to Eucampia, you'd know that surface water conditions were changing. You were having sea ice, then sea ice was going away, then sea ice was coming back. Another example of a biological proxy, these are foraminifera. For scale, they're about the same size as a medium grain of sand. These are scanning electron photomicrographs. So magnification here is probably 400 times or so. Now, both of these specimens are from a species called Neogloboquadrina pachyderma. And because that's a mouthful, people tend to call this N-pachy. Now, a specialist who looks at these can tell that as the specimen on the left was growing, it started out with this chamber, and then it added that one, and then it added this one, and then it added this one. So it added those chambers in a coil to the left as you look at the opening here. For comparison, if you look at the specimen on the right, there's the chamber, the opening, the aperture, and this one grew first that chamber, then a chamber to the right, chamber to the right, chamber to the right. So these are known as N-pachy left coiling and N-pachy right coiling. And what's really neat about this is that if you go out in the world today and you do a plankton tow in different parts of the oceans, you find that when the water is cold, polar, so probably about 5 degrees centigrade or colder, you'll only have N-pachy left. If the water's warmer than that, then you'll find N-pachy right. So even within just one species, the difference in the coiling direction can be used as a climatic indicator. All right, here's a generalized graph for a core taken from the North Atlantic. And what this is showing back to about 90,000 years ago is the variation in abundance of N-pachy left, which is that polar species. And so you see that there are times, which this author has highlighted with the sort of reddish or orangish color, when the polar species aren't very common. So that would be relatively warm times. And then there are times when N-pachy becomes the dominant foram that's present, and so we would interpret those as cold times. Now, N-pachy lives in the surface waters, so as you see these fluctuations taking place, it's really telling you about changes in sea surface temperature over time. So that will be an ocean climate indicator. In some cases, the people who work with the microfossils work with whole assemblages, and in that case, they can look at the characteristics of an assemblage today, decide what the temperature conditions are that that assemblage lives in today, and then go looking in the cores, the sediments, for other times when the assemblage was present, but perhaps in different locations. There was a project about 30 years ago called the Climatic Project, which tried to map out for the entire ocean what sea surface temperatures were like using this sort of plankton assemblage approach. And the diagrams that are shown here show you the change between today and 18,000 years ago, which was the last glacial maximum. And so you notice if it's a pale blue, that means there was little change from then till now. If it's a dark blue or a purple, it means that there was a fairly big change from then till now. And if we pay attention just to the Atlantic, notice that there's quite a large area of low to mid latitudes, which seems to have shown very little change. And there was more change at higher latitudes. Now, I do want to point out that more recently, some other studies have suggested that there actually was more cooling of tropical sea surface temperatures than the Climatic Project had identified. But I hope this at least gives you some idea about the strategy, the approach for using this kind of data. All right, the geochemical proxies, the oxygen isotope story is really the one that's used the most. You may know that water has, or that oxygen has two different isotopes, O18 and O16. They're both stable. They don't undergo radioactive decay. And out in the ocean, we have waters. Some of the water molecules have O18 in them. Some of the water molecules have O16 in them. Now, if you're going to move water up onto the continent by evaporation and precipitation in order to make big ice sheets, you have to evaporate that water out of the ocean. And when the evaporation is taking place, water that has O16 in it is more likely to be evaporated, just because it's a little bit lighter, so it's a little easier to evaporate. So as moisture is being transferred up to Antarctica or onto North America to build a big ice sheet, that water tends to be a little isotopically light. It's got a little more of the O16 bearing water than the original ocean did. That means that the heavier, isotopically heavier water tends to stay around out in the ocean. And so people would say that the ocean becomes isotopically heavier as the ice sheets grow. Well, that's fine, but how would we know what the ocean isotopic composition was at some time in the past? Fortunately, those little forams, as they grow, they secrete calcium carbonate, and the oxygen isotopic composition of the carbonate is actually determined by the composition of the water. So in a sense, the forams become the equivalent of our tape recorder. They are the place that stores information about the past oxygen isotopes. Oxygen isotopic record of the oceans. And so the isotopic composition of this foram carbonate is generally interpreted as a record of global ice volume. When the forams say that the ocean got isotopically heavier, that means that we had big ice sheets. When you melt the ice sheets, that heavier water comes back into the ocean, gets mixed around, and the forams will record a relatively isotopically lighter ocean. Okay, so a standard kind of diagram looking at this oxygen isotope record might look like this one. Don't worry about the notation. This is how the geochemists indicate the details of the measurements. But for our purposes, what's important is that to the left, a bigger number means that the foram carbonate is isotopically heavier, which means that the ocean was heavier, which means that there was more ice around. And if the curve goes towards the right, towards smaller numbers, that means that isotopically lighter water has come back into the ocean, which means that the ice sheets have melted, so we have warmer temperatures. Now, this kind of a record coming from the ocean can be very detailed. So you can see all the sort of spikiness that's going on through here. And it's that pattern of spikiness in these kinds of records that were really a key data set for identifying what are known as orbital or Milankovitch cycles of climate variability. And we'll talk a little bit more about that in just a second. In this particular record, I just point out to you that the lower part of the record has the changes going back and forth pretty quickly. And if you do some fancy statistics with this, you find that the predominant pattern of variability, if you want to think of it as a heartbeat, you can. The predominant heartbeat in here is 41,000 years. And then you'll notice that the equivalent of the EKG changes at somewhere between about 1 million years ago and 700,000 years ago. And then the heartbeat becomes much slower. We go into a pattern of 100,000-year cycles. And that's actually a change that's observed in lots of paleoclimatic records, this change at somewhere between 1 million years ago and about 700,000 years ago. So with this as a data set, people have then explored these so-called cycles, which are the orbital or Milankovitch cycles. And the orbital cycles are based on understanding that there are repeated changes in the shape of the Earth's orbit and the orientation of the Earth in that orbit around the sun. And so there's one pattern of change that takes about 100,000 years to complete. That's called the eccentricity. And over 100,000 years, the Earth's orbit around the sun goes from being something more circular to something more elliptical, and then back to something more circular. And as you change that orbit, you change the distance from between the Earth and the sun, and that'll have an effect on how much solar energy gets to the sun or gets to the Earth. A second pattern of variation is what's called the obliquity. This is the tilt of the Earth. Right now, the Earth's rotational axis is tilted at 23.5 degrees, but it cycles back and forth out to 24.5 and back to 22.5. And that's a cycle that takes 41,000 years. And then there's a wobble on that tilt, and that's known as precession, and that wobble is in a pattern that's repeated about every 20,000 years. So these are the so-called Milankovitch or orbital cycles. Climate scientists, astronomers, have calculated out for each one of these cycles what they would have done to the amount of solar energy reaching the Earth's surface from now into the past. And so this is a record going back about 1 million years, showing how precession, that wobble, would have changed the amount of solar radiation reaching the Earth, or obliquity, or the eccentricity. And if you combine these all together, you can then get what the pattern of solar radiation to the Earth has been back through time. In doing this, climate scientists tend to focus on the high latitude northern hemisphere, 65 degrees north, because this seems to be an area that's particularly sensitive to these kinds of changes. The other thing I want to point out, there are no numbers on here. So it's hard for you to tell right now, does this mean a doubling in the amount of solar energy, increased by a factor of 10? It's actually not that much. If you put real numbers on here, the low values would be around 400. The high values would be about 500. So as I mentioned off to the side, the maximum change in solar radiation is about 20% from the minimum up to these highest values. And yet that relatively small change in solar energy arriving at the Earth seems to be enough to have kicked us into big ice ages and pulled us out of big ice ages. And so people who think about this a lot have decided you can't really do that with 20% change. So there must be some amplifiers out there that take this relatively small change and make it have a much bigger effect. And it may not be a surprise to you that in today's world, the most likely suspects for those amplifiers are actually greenhouse gases. Okay, so we have this solar, these variations in solar energy arriving at the Earth's surface, and if you compare those to the oxygen isotope story from, say, the forams for when we had glaciation and when we had smaller ice sheets, we find that they actually cycle quite well in match with these changes in solar radiation. All right, and the last of the proxies to mention is iceberg-rafted debris, or IRD. How do we recognize these grains? Well, we tend to want to go to places that are far away from shore, at mid to high latitudes, where we think there may have been icebergs wandering around. And we tend to be, if we can, we like to be on top of offshore high spots. So seamounts are great places for us to do this kind of work. And in those settings, the most likely way we can think of for big grains to arrive is to have them be carried out by icebergs. And so we define ice-rafted debris as relatively large grains sitting in sediments that otherwise are quite small. Now, the icebergs are only released when glaciers get big enough to reach to sea level. And so our simple interpretation is that when we see IRD, or when we see more IRD, we think that there were more icebergs running around, and therefore the ice sheets got bigger. This is a very simple approach, but at least as a starting point, it's the way we tend to work. Now, the people who study glaciers in detail keep telling us that there are other variables at play. So we do know that there are things about the glaciers themselves that can affect how much IRD is going to be available. We also know that some oceanographic features, like currents, will have an influence on where the icebergs are carried. So if the currents aren't moving from the places where the icebergs begin to your site, you won't get any IRD. We also know that most of the icebergs tend to melt when they hit some kind of a boundary between cooler and warmer water. And so the distribution of ice-rafted debris may also be affected by the distribution of sea surface temperatures. All right, here's a picture that I had pulled off the web showing icebergs off of Cape York in Greenland. And scale is always an issue on these kinds of things, but I would be willing to bet that this long iceberg that I'm pointing out right now is probably several football fields in length. Most of these other ones, even some of these small ones, would probably be the size of a small to medium house. And remember that 90% of the volume of the iceberg is actually underwater. But in this picture, I'd particularly point out the ice that's over here, the ice that's up there. You can see the sediment that's sitting on top of the ice, or in some cases may actually be carried as layers within the ice. And when these icebergs undergo some melting, they often become unstable. They'll roll over, and as they roll over, all of this debris will then be turned loose and will make its way to the seafloor and be ice-rafted debris. Okay, in a core, this is a fairly easy piece of ice-rafted debris to identify. The meter stick scale here is in centimeters, so this particular piece of ice-rafted debris, which is much bigger than the rest of the sediment around it, is what, about 7-8 centimeters in length, so that's working on being 3 to 4 inches long. Some of you may have a geology background that would let you identify this as a piece of basalt, a dark, fine-grained volcanic rock. And by knowing that this is basalt and knowing something about the geology of the area around the North Atlantic where this was taken, and we can identify where this would have come from. And this piece actually came from Iceland. Not all ice-rafted debris is that big, though. You might notice that on the split face of this core, there are these little pits and marks. Those little pits and marks are made by little pieces of gravel or even pieces of sand, which are ice-rafted debris that have been disturbed as the core was being split. This kind of a core is split by pulling a wire through it, much like you'd use for a cheese cutter. And even little pieces of gravel or pieces of sand will get caught by that wire, drag a little bit, and leave behind sort of telltale footprints. But in order to study the sand-sized IRD in detail, we will take a sample and we'll wash away all of the fine-grained sediment, and then we look at the bigger particles. So this is sand-sized ice-rafted debris. That large sort of yellowish-looking piece, that's a piece of quartz with iron staining on it. These are pieces of granite. Here's a piece of quartz with no iron staining. And for comparison, there's a little 4am. So this is all sort of medium to coarse-grained sand. The case study that I wanted to mention briefly comes from some work that a former student and I did looking at sediments from these two sites off of Greenland. And I'd point out that in today's world, there's an oceanographic boundary that runs through here called the polar front or the Arctic front. And so you have cold water that's coming southward along or close to the coast. And we have somewhat warmer water that's out here offshore. So these two sites are, in today's world, actually a little different in their oceanography. Okay, we looked at ice-rafted debris from both of those sites. And first, just paying attention to the composition, we find that a lot of the ice-rafted debris at both sites was quartz. That could come from granites that are here. It could come from sediments that are up there. We had basalt, so smaller pieces like the big one I showed you. And that there's actually more basalt out here at site 919, which is offshore a ways. We also had coarse-grained acidic rocks. These would be granites, and also some of these sedimentary rock fragments like that iron-stained quartz, which we identified as coming from some old sediments that are here on the eastern side of central Greenland. And so the the ice-rafted debris is consistent with the geology that we find on shore. There's nothing unusual that we can't explain from onshore geology. And there's a little bit of a difference in the ice-rafted debris at the more onshore site versus the offshore site, which seems to be related to icebergs being able to make their way offshore a little bit and get down to Site 919 if those icebergs started farther to the north. So this is how we can trace the IRD back to a particular location. We also looked in more detail at Site 919. That's the offshore site. And so there are two sets of data shown here. The panel on the left you can basically consider to be the abundance of ice-rafted debris. On the right-hand side is the oxygen isotope curve for planktonic forams from that same site. Now, the people who work with these oxygen isotopes have identified particular patterns of change, and they've used those to define what they call marine isotope stages. And those marine isotope stages are numbered. So there's stage 1, then stage 2 isn't labeled, but it's the white band. Stage 3, stage 4 is the white, 5 is the gray. Now in this numbering terminology, the even numbers are glacials, and the odd numbers are interglacials. So in our simple prediction, we would expect that the ice-rafted debris would always be more abundant during the glacials, which are the white bands over here in the oxygen isotope curve. If you look on the left, you find that it's not quite that simple. There are times when the ice-rafted debris is very abundant in the white bands, but we also have times when it's abundant in the gray bands. And we have times when it's abundant right at the boundaries between white and gray. So what this has told us is that there's no unique link between ice-rafted debris abundances and global ice volumes. It's also pointed out that a number of the IRD peaks do take place at times of transition or very close to them. And this is actually an observation that's been made in a number of other cases as well. So the most dynamic times may actually be, most dynamic times for iceberg calving may actually be during times of transition. There's another piece of information here, though, that also highlights the effect of some of the oceanography. I hope you can notice that for each one of the glacials over on the left-hand panel, where we're showing IRD abundance, it says either east or west. East, this is information based on diatoms, and this is telling whether the polar front was to the east of the site or whether it was to the west of the site. If the polar front was to the east of the site, let's see if I can back up. If the polar front was to the east of the site, over here, then we would expect that icebergs would actually make it out to Site 919 before they melt. If the polar front is to the west of the site, then most of the icebergs will probably melt off towards the west when they first hit the warmer waters and before they hit Site 919. What we notice is that a number of the big peaks that occur during interglacials do occur during times when the polar front was to the east, here in stage 2, stage 10, stage 12, and stage 16. When we have the polar front being to the west during an interglacial, we tend to get less ice-rafted debris, probably because the icebergs melted before they got to the area, based on the sea surface temperatures. But then we have this sort of peculiar case, which is stage 6, when the polar front was to the east of the site. So we would expect that the icebergs would have been able to reach the area. Well, people who've worked in closer to shore and even on land on some of the record from stage 6 say that this was a time when there was lots of sea ice. Not so much sea ice during the other times, but this was a time with lots of sea ice. And the presence of that sea ice may have pinned the icebergs in close to the coast. So they weren't able to make it offshore to Site 919, even though the ice had gotten quite large. So the moral of the story is it's never quite as simple as we would have thought or hoped. we have other things that get in the way. And in this case, some of the other characteristics of ocean climate, like sea ice or sea surface temperature distributions, seem to have also played a role. We also have evidence for climate change at shorter time scales. In the North Atlantic, there's evidence for events that may have lasted 100 to 1,000 years or so. If we go back to this picture of the core that we saw previously, these color bands each represents a few hundred years to perhaps 1,000 years of deposition. And if you look at the record that comes from the forams, also in a North Atlantic core, you find that there are a number of these sort of shorter-lived events that have been labeled. And people who work on ice cores, particularly in Greenland, also look at oxygen isotopes and can interpret temperatures from that record. And you notice that they also have identified a number of these short-lived events. These are what are referred to as Heinrich Events, after a marine geologist who was the first person to describe them in the late 1980s. And what they have been interpreted to tell us is that for short periods of time, perhaps 100 to 1,000 years, there were tremendous quantities of icebergs that were being calved off of what's called the Laurentide ice sheet, which is the ice sheet that was centered in Ontario and drained out into Hudson Bay. And so you would have lots and lots of icebergs be released. These would float out into the ocean and release lots and lots of ice-rafted debris and also cause some other changes. These have actually been referred to as Armadas of Icebergs. There were some serious scientific papers that carried titles dealing with Armadas of Icebergs. Why would this take place? Well, the glaciologists, the people who study glaciers, have, in one case, developed a model that they call the binge-purge model, where the Laurentide ice sheet would gradually get bigger and bigger and bigger. That's the binge part. And when the ice got thick enough, it would actually press down on its base with enough pressure to melt the ice. This would be analogous to thinking about why ice skates work. You generate that thin layer of water because of the weight being on the sharp blade point. And so when the ice got thick enough and caused this kind of melting along the base, that would lubricate the base of the ice so you had less resistance. Then the ice would flow very quickly and produce or provide lots of icebergs out into the ocean. As the ice gets thinner, this is the purge part, or people say that the ice sheet collapsed. When the ice sheet got thin enough, then it no longer would cause that melting at the base. And so the ice would more or less refreeze to the bed. It would slow down, and then you'd go back into the binge episode. So the Heinrich events are interpreted as being the purging part of this binge-purge behavior. All right, so we've seen evidence for climate change at orbital and suborbital timescales. Melissa?
Yes?
Should we go ahead and stop now, or do you want me to keep going?
We have about 25 minutes left. I've only gotten one question so far, so if people want to, you can go for another few minutes, and if people want to type in their questions, we can get to those. Okay, all right. So we've seen evidence for this sort of climate change in the past at time scales of tens of thousands or hundreds of thousands of years, and at time scales less than that in things like the Heinrich events. What about future climate changes, and what kinds of predictions do we have out there based on science? Well, some of you may have seen this diagram before. This is a graph that accumulates lots of different information about what the Northern Hemisphere annual average temperature has been over the last 1,000 years or so. And I just want to point out that the 0 line on this curve is the average temperature from 1961 to 1990. So for much of this episode, much of the last 1,000 years, average temperatures were below
the average from 61 to 1990, with some variations in here, things like the so-called Little Ice Age. And then starting in the late 1800s, early 1900s, average temperatures start to rise and rise and rise. This is sometimes referred to as the Mann hockey stick curve, after Michael Mann, a paleoclimate scientist at Penn State, who first put this curve together. Now, you're probably not surprised to see that people have also looked at the concentrations of greenhouse gases, especially CO2, in the atmosphere over that kind of time. Now, people who study ice cores have an advantage over those of us who study sediment cores, in that the glacial ice actually has bubbles of ancient air trapped in them. So they can measure directly on those bubbles of ancient air what the CO2 concentration was at times in the past. And if they do that for some of the oldest ice that we have around, going back 400,000 to 800,000 years ago, you see this sort of EKG that we were talking about before. But notice that during the warm times, the interglacials, the naturally highest occurring CO2 content was only about 280 parts per million. If you now look at the blown up panel up here in the top, for the last 1,000 years, CO2 contents were at about 280 parts per million until the beginning of the Industrial Revolution, and now they've gone up to the point where now, if I remember correctly, within the last month or so, they're on the order of 390 ppm. So this is the human-induced CO2 from the burning of fossil fuels. The best evidence I know of that links or demonstrates a cause and effect between greenhouse gases and warming, rather than a simple correlation, is work that was compiled by this group called the Intergovernmental Panel on Climate Change, the IPCC. Their fourth report came out in 2007. Their fifth report will be out within the next year or so. And in this case, they've brought together information from about 10 of the best climate models that have been developed by different groups of scientists all around the world. And every one of those models was developed in a slightly different way. So they don't all deal with the system in exactly the same way. So if they give similar results, that suggests that there's some underlying value to the conclusion. Well, in the upper left-hand panel, if you run these models and you simply let variations in things like sunspots or variations in volcanic activity, which put aerosols in the atmosphere, if you let natural forcing only take place, the models predict that temperatures should have done what's shown by the gray line down here, when the observations show the red line increase. If you run those climate models putting in the CO2, so this is the human-produced forcing, you get a much closer fit between the model results shown in gray and the red line, which is the observations. And if you put both of them together, the natural and human-produced causes, you get a very good overlap, which suggests that the models actually have this just about right. The IPCC report also makes predictions that you might already be aware of for changes in temperature over the next century. And the different results that are shown here are for different climate models. But the sort of average of most of them predicts that we'll have temperature increases on average of somewhere between 2 and 2.5 to 3 degrees centigrade. There are some extreme cases that suggest 4 to 4.5 degrees, but the sort of consensus is in this 2 to 3 degree range. Now, that's only a global average. The climate models can also be run to look at or make predictions about the geographic distribution of that change. And this is an example that's shown. The overriding color in all of this is at least something in the sort of pale orange, which is in the 2 to 2.5 degree range. And notice that the oceans tend to show less change than the continents do. That's because of the ability of water to absorb energy without changing temperature so much. If you look on the continents, there's more temperature change, and especially areas that are already quite warm show higher changes or more temperature increase than areas that presently aren't quite so warm. But the bells and whistles, the alarm bells, really go off when you notice what's projected for the high northern latitudes. This sort of purple color means temperature changes of 6 to 7 degrees centigrade in surface temperature. This is why people, climate scientists, often refer to the Arctic region as the canary in the coal mine when it comes to global warming. All right, going along with the changes in temperature are also probable changes in the distribution of precipitation. You can run the climate models and they'll tell you about projected distribution of precipitation as well. I mean, in this case, blue colors mean an area gets wetter. Yellows and browns mean it gets drier. And the bad news is that lots of places that already are pretty dry, Southern Europe, the American Southwest and California, Southern Africa, Western Australia, they get even drier. Northern India gets even drier. Some places do get wetter, but they tend to be places that are already fairly wet. So this is the reason why policymakers, climate scientists, are really worried about water security for the future as much as food security. All right, sea level rise. Lots of people have probably already heard about the projections for sea level rise. Again, using these climate models, the average projected sea level rise by 2100 on the order of half a meter or a little bit less. But I would point out that that's a projection based just on warming the water. Even back in 2007 when this report came out, some of the glacial geologists or glaciologists started to say, well, with this kind of warming, it's quite likely that at least some glaciers and parts of the large ice sheets would undergo some of these changes so that they start to flow faster. And if that happens, much like the Heinrich Event story, you're dumping lots of water back into the ocean that used to be stored on land. So even 4 years ago, some of those glaciologists were saying that this number probably underestimated sea level rise by a factor of 2 or 3. And in the time between 2007 and now, quite a few of the paleoclimate scientific community has come to agree that this projection probably underestimates what the sea level rise is likely to be. In all of these cases, you have to make some assumptions to run the climate models. You have to make some assumptions about what the CO2 contents will be. And depending on how the burning of fossil fuels goes into the future, CO2 could go up by a little or it could go up by a lot. And if you go with that range of scenarios, then the temperature change can go from, say, the 2.5 degree average value that we talked about before, up towards the 4 to 5 degree centigrade value that's sort of the worst case scenario. So I hope that has given you some idea about how we can read past climate out of sediments, particularly ocean floor sediments, and that it then gives us some insight for looking in towards the future and helping to guide what some of these projections might be.
Oh, okay. Well, thank you, Larry.
Yep.
I know we have one question, but I would urge people, we've got about 13 minutes left, so if you have a question, please type it in. You really actually need to ask him your questions now because Larry's heading off to sea soon. So in a few days, he'll be off to sea for 2 months or?
Yep. So yeah, on Wednesday, this coming Wednesday, I will head to the Azores, which are a set of islands out here, where I'll get on board the Resolution for a 2-month cruise. We will be drilling a number of sites here on the Atlantic margins of Spain and Portugal. And the primary goal of this cruise is to look at the outflow of water from the Mediterranean into the Atlantic. So in the cruise logo, which is down here at the bottom, this MOW, that's Mediterranean outflow water. And the water coming out of the Mediterranean is actually quite salty compared to open ocean water. And it's the input of that extra salt into the North Atlantic that helps to prime the pump, so to speak, for the so-called Great Salt Conveyor. So this is a diagram showing some of the paths of this Mediterranean outflow water. It flows below the surface, about 1,000 meters down, and in some places tends to hug the continental margin, so it actually leaves a record in the sediments that we're hoping to explore in more detail. This part of the ocean being what it is during the wintertime, we may encounter things like this or more. The last of these cruises that I was on was in 2004 off of Greenland in September and October, and this was a moderate storm, so 30-foot waves and 60-mile-an-hour winds. If we have anybody from Alaska, I know that's fairly small compared to the storm you guys have had move ashore recently, but we may have to deal with some of that. We sure hope that we'll see a lot more that looks like this rather than storms.
Okay, well, we have a few questions, so
okay.
Let me get to them. Okay, so one question is about when you were showing the Milankovitch cycle, they were asking what factors actually affect the Earth's tilt?
The tilt? Let's see. Let me see if my rule will work. Where did it go? There it is. Okay, so my understanding of this is as a user, not somebody who actually does these kind of calculations. My understanding of the origin of all of these styles of motion, eccentricity, obliquity, and precession, is that they're basically all they've been set in play from early in Earth history due to interactions with other planetary bodies, so the sun, the other planets, and I guess also the distribution of mass within the Earth. I'm not sure if that answers the question, but that's my understanding of these is that they're not something that has just started in the last few million years. And in fact, there are people, geologists, who work on certain kinds of sediments up on land that are hundreds of millions of years old, in a few cases even billions of years old, and they think that they can identify variations even in those very old sediments that are linked to Milankovitch cycles. So this behavior has been in existence for essentially all of Earth history that we can tell.
Okay. Another question was, what were the temperature changes experienced by the marine environment in the mid to low latitudes during the Ice Age periods in northern latitudes?
Okay. So the more recent data, let's see, let's go back to that. So this guy. Yeah, the more recent data, well, let's back up. The Climap results, they would have said that the tropical waters, lowish latitudes, surface waters in the Atlantic, probably cooled by no more than 1 degree centigrade. More recently, the story has been that even the low latitude waters may have cooled by 3 to 4 degrees centigrade. And if for comparison, the high latitude waters probably were cooling by 5 to 7 degrees centigrade. So in the original interpretation, 1 degree change down here, 7 degrees change up there. That's a really big, that establishes a really big, what's called a gradient rate of change from low latitudes to high latitudes. The more recent data suggests that that gradient was not as steep. So if you cool more down here and you still cool about 7 degrees up there, it's cooler overall, but you don't have that really big difference from low latitudes to sort of the area off of the Canadian Maritimes during the glacials.
Okay, the next question is, you said earlier that you can tell the general direction and strength of wind by using surface currents and upwelling. Can you use lower currents by calculating for Ekman's spiral, for example?
Boy, probably not, because the Ekman spiral is best developed in waters that are relatively deep, and so whatever would be happening at the base of the Ekman spiral is not dragging along a bottom, so it's not able to leave a particular record. Now, there are some of the other indicators that we talked about that can be applied to interpret what was happening to the really deep currents. So like the strength of currents that flow along the continental margins at several thousand meters depth. These are referred to as boundary undercurrents, so western boundary undercurrents and eastern boundary undercurrents. And there are ways to look at characteristics like the sizes of the sediment particles and how aligned or not aligned they might be to tell you about those deep currents. But it's really a bit of a challenge to say anything about currents at some of the midwater depths because they're not generally in contact with a bed, the bottom of the sea, where it's going to leave some kind of a record that gets preserved for us.
Okay, another question was, how does climate affect turbidite deposits and turbidity flow, particularly off the west coast of North America?
Ooh, boy. Boy, that's a great question. There are, I can think of two ways that there's an influence, but they're both somewhat indirect. Turbidity currents tend to occur when you've got quite a bit of sediment coming in off of land, and so that sediment supply from land, particularly in a case like the west coast of North America, where the continental margin is fairly narrow, that's going to be affected by characteristics up on land, like how much precipitation there is and what the temperatures are, which will affect the weathering rate up on land. So you'd really have to be worried about during a glacial, you know, was it an area that got wetter on land or an area that got drier? So that's one of the effects, but it's going to be an effect that starts up on land and gets transmitted out into the ocean. The other effect, though, and this is true on more or less all continental margins, not just the west coast of North America. During ice ages, like the last glacial maximum, sea level actually fell by about 130 meters. And around much of the world, what that means is that almost all of the continental shelf that we think of today was actually exposed. And so streams and rivers, in those cases with sea level lower, the streams would have actually carried the sediment out almost to the shelf slope break. And when those sediments were deposited, they were essentially right at the top of the slope that they would head down as turbidity currents. So on many margins, you actually find that turbidity current influence increases during the glacials, primarily not because of a direct climate influence, but because sea level fell, so the sediments were being transported out to the top of the steep part of the slide, rather than having, as they do today, they get dumped up on the shelf and they have to make their way across the shelf in many cases before they can head out into the deeper ocean as turbidity currents. But that's a really good question. There are lots of people who've been interested in sediment during glacials getting deposited in what are called submarine fans fed by turbidity currents. And during the interglacials, when sea level is high, the sediment tends to get deposited as deltas up on the shelf. So in many settings, off of the mouths of big rivers, say like the Mississippi, you actually have a delta, and then further offshore is the submarine fan. And the activity kind of cycles back and forth between those two locations, depending on whether sea level is high or sea level is low.
Okay. Another question is asking, can we assume that more carbonate in a core equals more productivity, which also equals warmer waters? And therefore, darker means less productive and cooler glacial? Or is that too simple of an assumption?
That's pretty simple, yeah. Because there's another side to the carbonate story if you're talking about plankton in the surface waters producing carbonate skeletons and then having those skeletons settle towards the seafloor. And the other part of the story that we haven't talked about is the fact that a lot of carbonate, or there is the possibility to have a lot of carbonate dissolved in the deep ocean. There is a level within the ocean called the carbonate compensation depth, or the CCD. And the carbonate that's settling through the water column all gets dissolved by the time it reaches that level. So if you take a series of cores down the flank of a mid-ocean ridge, above a depth of somewhere between 3,000 and 4,000 meters, you'll have lots of carbonate. And when you get below that level of 3,000 to 4,000 meters, depending on which ocean you're in, there's no carbonate, and that's because it's been dissolved away. And the complication comes because that CCD level also migrates up and down through time, usually controlled by things that are happening at high latitudes that influence the speed at which deep waters flow around the ocean basins. So if you're in a setting where you don't have to worry about CCD changes, then you could go ahead and use the carbonate abundance as a productivity indicator. But unfortunately, this dissolution changing the level where it does its ultimate job, as that changes through time, that complicates the story a bit.
As you were answering that question, something came in. They say you may have just answered this, fan versus delta. How do scientists differentiate between glacial sediment deposited by melting compared to massive ice sheets melting the lower layer, when you were talking about the ice skating analogy?
The ice skating analogy. The water, if I understand the question correctly, the amount of water that would be produced by that melting at the base of the ice is really, really, really small compared to the amount of water that would be released by the glaciers calving the icebergs and the icebergs flowing out and melting. If you look at that kind of a meltwater layer at the base of glaciers today that have them, that meltwater layer is at most perhaps a few meters thick, and you're turning loose icebergs that are hundreds of meters thick. So most of the water, the vast majority of the water that would be turned loose into the ocean during one of those kind of events would come from the melting of the icebergs, not from the water flowing along the base of the ice. Does that sound like the question that the person was asking, Melissa?
I think so. If they're still on and they still have another question, they can
please
type it in quickly.
Yeah.
I have two remaining questions. If you go back to your cycles image again, they're asking, where are we on the eccentricity orbit?
Ooh, boy.
Currently. Do we know?
Yeah. Oh, yeah, we know. So I'm just going to have to go from what these diagrams show. Eccentricity would say that we must be in a fairly stretched out part of the cycle right now, because the eccentricity contribution to the amount of solar energy that we're getting is shown as being low. And that happens when you go to the more sort of egg-shaped ellipse. So when we're out here, then we pick up less solar energy, and you don't make up for it during these sort of closer passes.
Okay. And the last question was, how many cores will you drill during your 2-month time at sea?
Oh, far too many. Let's see. A lot. Let's see. These locations, these sites, are all in relatively shallow water. The deepest site that we're going to be drilling is this guy up here, which, if I remember right, is in about 2,000 meters of water. All the rest of these sites are in 1,000 meters or less. At least for the shallow parts of the sites that those sites that we'll be drilling, so the shallow sediments, we use a system that is driven by water pressure rather than any kind of a rotating bit that cuts into the ground. And this hydraulically driven corer sort of pushes out in front of the drill pipe and takes the core. You can take that core within 10 minutes or so. And so the slow part of the job is getting the pieces of coring pipe moved up and down from the seafloor. And if you're in 1,000 meters of water, it takes about 10 minutes to get the tool down. It takes 5 minutes to take the core, and it takes 10 minutes to get the core back up. So, every half hour we could be taking a core, and each core is 9.5 meters long. None of these sites is very far from one another. The operational plan, I think at most we have like 2 days steaming between these two sites. The rest are all, less than a day. So we're likely to be coring all the time and getting a lot of core. I think they're estimating that we could get at least 5 kilometers of core. So that's about 3 miles of core.
Wow.
We'll be busy.
Yeah, you're going to fill the repository, aren't you?
Yep.
Okay, well, it looks like we've had you answer all the questions.
Okay.
So on behalf of everybody who participated tonight, I'd like to say thank you very much for being our first presenter for this year's webinar series.
And I'd like to say you've been a great audience.
Yeah, you've been a very quiet audience because we've had them on mute.
It's a little odd from my perspective. I'm used to looking at students and getting some feedback, so I hope things have gone smoothly.
Oh, oops, let's see. We got, whoops, what did I do? I think I deleted the question, but I think what I saw was that somebody wrote that they said thank you and that they thought it was going to be very helpful in teaching their students as well. And earlier, one person had noted they said bon voyage on your trip.
Well, thank you.
Okay, so I'm going to actually take control of the screen just very quickly.
Okay.
Let's see, is everybody showing? Let's see, show my screen. See if everybody sees. Okay, if you're seeing my screen now, I just wanted to show everybody where the professional development webinar series is on the NOSB website. If you just go to professional development all the way on the left, this year's information comes up. And I just want you to see this page because we have Larry's information up, and we will be posting both his PowerPoint presentation as well as the recording of this webinar. So we highly suggest, for the NOSB coaches, to have your kids come back to this website and, listen in on the webinars. And if there's any resources, and they can go through the presentation, the PowerPoint as well, to learn a little bit about the talk tonight. And also to show you that our next presentation is going to be on November 21st. That's a Monday. It's going to be at 8 p.m. again, Eastern Time. And the next one is on phylogenetic trees. It's Alan and Jennifer Collins. And Dr. Alan Collins has an interest in jellyfish, so he's going to go over the evolution of jellyfish. And Jennifer does a lot with the Deep Earth Academy and education, and she's going to show you how to use and why you use phylogenetic trees and give you some tips in using them in your classroom and helping your students understand them as well. So just to give you a brief update, let's see, we have a few people are still hanging on. Were there any last-minute questions? I see one note saying, again, thank you for your presentation. Are there any other last-minute questions before we let Dr. Krissek off the hook? Let's see. Yes, we have one question. No, they say no. Okay. Well, again, thank you, everybody, for participating, and we will talk to you all on the 21st. So thanks again, Larry.
Okay, no problem. I probably will talk with you before I take off.
Yes.
Okay.
So good night, everyone.
Right. See you.
Bye.
Bye.